Swayam Prabha. Digital India. Educated India.
I have got in front of me certain geometrical shapes. For instance, this is called the cube, this is the octahedron, this is the tetrahedron, this is the dodecahedron, and this is the icosahedron. One thing which might be obvious looking at these shapes is that these are not irregular shapes. There is a certain regularity to them. For instance, every face of this solid is triangular. At every vertex of this solid, you find there are 5 triangles which come together. If you look at this solid, for instance, you find that every face is actually pentagonal, and at every vertex you have 3 of these pentagons coming together. So, there is some inherent beauty in these solids. In fact, this shape, the dodecahedron, was considered the crowning glory of Greek civilization, and therefore, these kind of solids appeal to the human mind. So, what is that we have in common in all these solids, and how can we understand these solids from a language which is the language of symmetry, is what we are going to consider in this chapter. So, we will take up the concept of what is known as symmetry operators. We will talk about symmetry operations like translation, rotation, inversion, etc., and we will briefly introduce the concept of point groups. For students interested in more detailed and advanced reading, the classic text by M.J. Berger on elementary crystallography is worthwhile reading. The first question, of course, we should ask ourselves is, why study symmetry? Now, suppose I look at a crystal, what we call a well grown crystal, and on the bottom there are 2 crystals which are shown here, one on the left hand side and one on the right hand side. The one on the right hand side is a potassium diphosphate crystal grown from solution, and you are immediately you notice the beautiful symmetry of the external faces which are forming. And this is one of the important characteristics of well grown crystals, that they have an external symmetry or an external shape or a form which is well defined. And crystals form an important class of materials, and therefore, the language with which you describe crystals is in fact the language of symmetry. And additionally, it would be worthwhile noting, even quasi-crystals are defined and described based on the language of symmetry. Of course, in the current context, the symmetry we are talking about is what is known as the geometrical symmetry, and of course, there are generalized versions of symmetry in physics which we shall not be dealing in these set of lectures. An important point, another motivation why we need to study the symmetry of a crystal is because any given property of the crystal, it could be a refractive index, it could be any other property like conductivity, has a symmetry which is at least the symmetry of the crystal. Typically, it could have a symmetry higher than that of the symmetry of the crystal, but it at least has the symmetry of that of the crystal, and this is known as the Neumann principle. And as we have seen from the example of the crystal which is shown below, that one of the obvious manifestations of symmetry inherent in a crystal is the external shape of the crystal. And that is why when we want to describe crystal, the best language is the language of symmetry, and which is the crux or the core of the language of crystallography. Symmetry, in conjunction with other elements, help us define an infinite crystal in a very succinct or terse manner, and that is one of the reasons why we take up crystallography, which is centered around the concept of symmetry. Now, there are a lot of concepts we will be introducing during the course of this set of lectures. Those concepts involve concepts like lattices, motifs, the unit cell, etc. But before even we introduce those concepts, we should note that when we are talking about symmetry, it could be the symmetry of any one of these entities which could be under consideration. So, suppose I could be talking about the symmetry of the crystal, which is what is primarily important, but in certain specific contexts, for instance, we could be talking about symmetry of the lattice or the symmetry of the motif or the symmetry of the unit cell, and that is why when a description of symmetry is being made, it is very, very important to note under what context, what is the central focus of the description which is being kept in mind. Additionally, we could also be talking about the symmetry of the growth of an external shape which we considered. For instance, this crystal has a certain symmetry, and we could be describing the growth form of the crystal, which also would be coming under the class of symmetry descriptions. An object is supposed to possess symmetry when, if it is brought into self coincidence after some operation, then it is said to possess symmetry with respect to that operation. Now, for instance, the obvious symmetry which we are all accustomed to, for instance, is the human face or the human body. Externally, it has got an approximate mirror symmetry. That is, if you place a mirror in the center of the body, then you will see the left hand side reflects to the right hand side, or equivalently the right hand side reflects to the left hand side. Of course, this is an approximate external symmetry that we have got, and additionally the human mind is well tuned to appreciate symmetry in any body. And as the ancient Greeks had done, they had in fact come across these solids which are known as the Platonic solids, which I had described some time back, the cube, the dodecahedron, the icosahedron and the tetrahedron, and therefore there is a natural ability of the human mind to appreciate symmetry. But in this context, we will take up symmetry in a more formal way, a way which is ideally suited for describing crystals and the other entities we had talked about in the previous slide, like unit cell, lattice, etc. So, if an object is brought into self coincidence after some operation, it is said to possess symmetry with respect to that operation. So, naturally question is that what is a symmetry operator? Given a general point, a symmetry operator leaves a finite set of points in space. That is, if I have a symmetry operator and I have a general point in space, then at the end of the symmetry operations, you end up with a finite set of points. And in other words, you can describe a symmetry operator as that which closes space into itself. Later on, we will be talking about symmetry operators which involve translation, and in that case we will have to assume that it leaves a finite set of points within the unit cell, which is another concept we will be dealing with later. But essentially, as you start with a point, then the symmetry operator acts on that point, creates a finite set of points, and typically this finite set of points we are referring to is within the unit cell. Of course, the question we sort of alluded to, we can ask more formally, that why do I need to talk about symmetry and symmetry operators? If an object, for instance a crystal, or it could be another general object which is under consideration, has some symmetry, then we need not go ahead and describe the whole of the object. We can just describe a part of the object in conjunction with the symmetry operators, and I will get the whole object. In other words, I am conserving my information or conserving my labor in describing only part of the object in conjunction with the symmetry that the object has got. Therefore, I will get an entire object without having to describe a lot or prescribe a lot of information. For instance, I have got a square here in my example, and this square has a mirror symmetry. We will formally deal with what is a mirror symmetry, but we all know from our common sense experience, we know what is a mirror. So, the mirror, for instance, would reflect the left hand side of the blue rectangle into the right hand side, and therefore create the entire square. Additionally, we could also imagine a horizontal mirror which is present, which means that this horizontal mirror can actually reflect the top part of the blue rectangle to the bottom part, which I will describe here. So, this part is reflected to the part below, and therefore I will get my entire blue rectangle. In other words, instead of working with the entire square, I can work with half the square or quarter the square, and these two mirrors will produce all the 4 quadrants of the original square. Additionally, if I notice, this object additionally has a mirror which is the diagonal mirror, which is shown in the figure on the right hand side. So, if further I do not have to describe the entire what you may call 1/4 of the square, I can actually describe one triangle in conjunction with this mirror, which will produce this square. In other words, what I have done is that all I need to prescribe is this one triangle, and this triangle in conjunction with these 3 mirrors, the one diagonal mirror, one vertical mirror and one horizontal mirror will give the entire blue square back to me. Therefore, I have conserved my information, or I have described my object into the least part conjunction with the symmetry operator, symmetry present in the object, and therefore I get my entire original square. As we shall see soon, there are other symmetry operators which we could invoke. For instance, what is something known as the fourfold axis, which could also generate my original square from one quadrant of the square. In other words, the language of symmetry to be in is used so that we can be very terse in our description, so that we can supply minimum information and generate the maximum amount of knowledge possible. This is very, very useful because typically crystals are infinite, and many crystals we will be talking about have very many number of atoms inside them, or for instance there could be ions present in crystals, and I do not want to be prescribing the position and the type of ion present for hundreds of them. So, I can actually conserve my effort by putting the minimum required information along with the symmetry present in the system. How can I classify my symmetry operators, and what kind of symmetry operators exist is the next question we will try to address. So, based on dimension of the operator, based on if the symmetry operator takes the object to its mirror form or not, based on the fact that if the operator acts at a point or moves a point, or if it plays a role in the shape of the crystal or not. For instance, is it microscopic or is it macroscopic? So, I have multiple ways of classifying symmetry operators, and therefore coming to know of the very many different kind of symmetry operators which are present, which are especially relevant to crystals. So, to summarize once again this slide, so I can classify symmetry operators based on the dimension, based on if it takes an object to its mirror form or not, based on the fact that if it leaves an object around a point or moves it from place to place, or if it has any role to play in the external shape of the crystal or not. So, we have certain symmetry operators whose names are on the right hand side here, for instance the translation, the rotation, the mirror and the inversion, and further we will see that there are other symmetry operators like roto-reflection and roto-inversion. We shall be taking up some of these very soon, but this is an attempt to give a broad overview and classification of all the possibilities. So, there are type 1 symmetry operators which take to an object to its same form, and there are type 2 symmetry operators which take an object to its what is known as the mirror form or the enantiomorphic form. Now, it's to understand what is a mirror form, the best example we can consider is our hand, the human hand. So, we got the left hand and the right hand. I can perform no rotation or translation operation to make my left hand coincide on top of the right hand, because my left hand and right hand are related by a mirror operation right in the middle of my two hands. Therefore, there is no possible translation or rotation object which can take my right hand to my left hand, or equivalently my left hand to my right hand. So, these are two different kind of objects, and one is if you call the right hand one, the other one is the enantiomorphic form or the left hand one. Therefore, there are symmetry operations like mirrors and inversion which take an object to its mirror form or the enantiomorphic form. So do roto-reflection and roto-inversion, but a mere translation. For instance, suppose I just move my hand by a certain distance, such an operation will not take an object to its mirror form. So doesn't rotation. Suppose I rotate my hand, I still end up with a left hand and not a right hand. I can classify my symmetry operators based on the dimension of the operator. For instance, inversion is a 0-dimensional operator, rotation is a 1-dimensional operator, and mirror is a 2-dimensional operator. And of course, this dimension is assuming that our whole space in which we are working is the 3-dimensional space and not a lower dimensional space. These aspects shall become clear once we actually take up these operations and see how these operations have an effect on space and have an effect on points in space. So, we can classify symmetry operators based on if the symmetry operator takes an object to its mirror form or leaves it in its original form. Symmetry operators can also be classified based on its effect on the external shape of the crystal, and therefore we talk about macroscopic symmetry operators and microscopic symmetry operators. Screw and glide reflection, for instance, which we will take up much later in the describing of symmetry, do not have any effect on the external shape of the crystal. They involve translations, the screw and glide reflection, which are of atomic dimensions, and therefore, or dimensions of the order of lattice parameters typically in crystals, and therefore, they have no effect on the external shape. While on the other hand, rotation, mirror and inversion, which are the three macroscopic symmetry operators, have an effect on the external growth shape of a, or for instance the external equilibrium shape of a crystal. Additionally, we have to note that there are many symmetry operators available to us, but some of them are absolutely necessary to describe a crystal, while some of them could be redundant. In other words, I can get away by not using all the symmetry operators which I had described so far. For instance, suppose I want to describe a crystal, I can work with rotation and mirror and not in fact invoke inversion at all. Otherwise, I can actually work with rotation and inversion, I cannot invoke mirror, for instance. So, there is a possibility that I can work with a lower set of symmetry operators than actually available in the crystal, and this was also obvious from the example we considered before. For example, this square, the blue square, had one horizontal mirror, one vertical mirror and one diagonal mirror. But we saw that actually it additionally has some other symmetry operator which we called the fourfold axis, but I did not have to invoke the fourfold axis to create my full square. Therefore, there are some additional redundant operations which also might be present, which I need not invoke. If I want to generate all the symmetry acting at a point, then the bare minimum I require is rotation and something known as the roto inversion. And in this case, of course, I am at a point, I am not moving from one point to another in space, and these points remain localized, and we land up with a finite set of points at the end of what is known as allowed combination of operators. But on the other hand, if you are talking about glide reflection screw, then we end up actually moving the point and land up with an infinite array, but within an unit cell there will be only a finite number of points. So, what is the first operation which we need to consider, which is very relevant to crystals, because every crystal has at least guaranteed one minimum symmetry associated with it, which is the translation. And in fact, the very definition of lattices which we will come across later is based on this operator, which is the translation operator. A translation operator just simply moves a point by a certain vector t, and in 3-dimensional space actually you could have 3 different components along the 3 basis vectors. Here is an example below in the figure in which I have a 1-dimensional crystal in which I have the crystal being created by a 1-dimensional translation operator, the t vector. Therefore, I have a lattice point, from this lattice point I generate another lattice point and so forth. Therefore, if I have this translational symmetry, it does not matter to me where in this array I am sitting. For instance, if I am sitting at this point, the entire space would look exactly identical as if I were to sit in a different point to its left, for instance, at this point. Similarly, if I have a crystal here, and in this crystal, which is now consisting of pentagons and which has got translational symmetry, it does not matter if I am sitting at point A, which is here, or at a point B, which is here, or at a point C, which is here, and entire space will look identical to me, and that is why it is this crystal is expected to possess or is supposed to possess translational symmetry. And what does the translational symmetry do? It actually produces a periodic array of points starting with a single point. And if you start with an object, it will produce a periodic array of objects, and this translation could be in 1 dimension as in the example below, it could be in 2 dimensions or could be in 3 dimensions. Therefore, if I have translational symmetry, I do not have to describe the entire crystal. All I have to do is take up, for instance, and one unit of the crystal, for instance this pentagon, and in addition to this pentagon I can describe a translational vector t, and I will land up with the entire crystal. So, there is a certain advantage, certain brevity, certain succinctness when I use symmetry operators to describe crystals. The next symmetry operator we consider is the mirror and the inversion. The left hand side shows a mirror operator which we had of course briefly considered just now, and the right hand side shows a inversion operator. Now, as I had pointed out, suppose I have my 2 hands, I can visualize a vertical mirror plane between my 2 hands. On the other hand, suppose I place my 2 hands like this, that is my one hand is above and then one hand is below, then I can think of an operation which is an inversion operation right at the middle of between the 2 planes in which my 2 hands exist. Therefore, both of these operators, my mirror operator and my inversion operator, take an object to its enantiomorphic form or take an object to its mirror form. The mirror is a plane, therefore, it is a 2-dimensional operator. In 3-dimensional space, my mirror is actually a plane which takes my left hand to my right hand, while the inversion operation is actually a point. So, inversion is 0-dimensional, mirror is a 2-dimensional operator. So, the 0-dimensional inversion operator again takes my left hand to a right hand, but as you can see that a point x, y, z becomes minus x, minus y, minus z when an inversion operator acts on it. So, these are two ways of taking an object to an enantiomorphic form, but given the dimensionality, it is clear that they are not identical, and also given its effect on a general point. How a mirror acts is that suppose I had a point here which is at a plus x, then the mirror operator takes it to minus x, but leaves it at the same distance y height. On the other hand, an inversion operator takes an object which is at point at plus x plus y plus z to a point which is right below here, which is minus x minus y minus z. So, if you take which is also shown in a diagram right here below, if I start with an vertical mirror here and a right handed object which is above the plane of this sheet, then the right hand object is taken to its left handed object by the mirror plane. Of course, you could have an horizontal mirror as shown here, in which case you will start at the point which is, say for instance, a green right handed object above the plane is taken to a red square which is actually below the plane by an exact distance, which is, if this were at a distance of plus z, then this red square would be at a distance of minus z from the plane. On the other hand, the inversion operator, as I pointed out, is a 0-dimensional operator which takes a right handed object to a left handed object, the right hand object being above the plane and the left hand object is below the plane as shown here. The next operation we consider here is known as the rotation axis. In the case of the rotation axis, if you start with a general point and an axis which is known as the rotation axis, it rotates a point and leaves a finite set of points. Now, and what you call an n-fold rotation axis is a rotation axis which rotates a point by 360 degrees divided by theta. Therefore, if you have a 4-fold axis, then the rotation angle theta would be, for a 4-fold axis, on the other hand, suppose I am talking about a 3-fold axis, therefore, there is a characteristic rotation associated with every axis which is an n-fold axis. In general, of course, you would notice that I can actually start with a single point and land up with a finite set of points if I have an axis of rotation, and this n could actually be any number starting from 1, 2, 3 all the way up to some higher numbers up to infinity. But then in the description of crystals, we are especially concerned with those rotations which are compatible or consistent with translational symmetry or the basic inherent symmetry of crystals, and when we are putting this restriction, of course I am not showing the proof here, you would note we will land up with only certain allowed rotational symmetries. So, in general, and we could have an n-fold rotation axis which is having any value of n like 1, 2, 3, 4, 5, etc. But then when you are talking in crystallography, we want to consider only those rotation axes which are compatible with translational symmetry, which is a basic requirement of all crystals, and in that case we will only consider, for instance, the 1-fold, which is a very trivial rotational symmetry, the 2-fold, the 3-fold, the 4-fold and the 6-fold rotation axis. In other words, I do not have to consider the entire set of rotation axes, which includes, for instance, there is no 5-fold involved here, there is no 5-fold here, there is no 7-fold here, there is no 11-fold, etc., etc. Therefore, there is only a small finite set of rotation axes I need to consider when I am talking about symmetry, rotational symmetry, which is consistent with translational symmetry or that which is consistent with crystals. Therefore, future focus will be on those rotations which are compatible with translations, which are the 1-fold, the 2-fold, the 3-fold and the 6-fold rotation axis. So, let us try to understand what this rotation axis is and what it does to a general point. Now, a 2-fold rotation axis is an axis, for instance, which is perpendicular to the plane of the figure shown here. For instance, this is my circle, and a two-fold rotation axis which has got a symbol as shown here. It has got a lens type of a symbol, and this rotation axis is perpendicular to the plane of the slide. This rotation axis therefore is a one-dimensional axis. We had previously seen that the mirror is a two-dimensional plane, the inversion is a zero-dimensional point, while a rotation axis is a one-dimensional line. And what does it do? For instance, a two-fold axis due to a point, for instance, the green circle, which is above the plane of the slide. What it does, we know that n is equal to 2 implies that the rotation is therefore a two-fold rotation axis rotates a point, and therefore the entire space for that matter by 180 degrees. Therefore, it rotates this point and takes it to this point. So, I start with point 1, it produces point 2, and a further action of that finally closes space on itself and comes back to 1. Therefore, irrespective of how many times this rotation axis operates, it is going to leave only 2 points in space, and this is an important point to be noted. Similarly, if you look at a three-fold axis, a three-fold axis would mean a rotation of 360 by 3, which we had seen before, which is 120 degrees. 360 by 3, I am sorry, which is 120 degrees. And if you start at the general point 1, then a three-fold rotation axis, which is got a symbol of a filled triangle, takes it to a point 2, which further takes it to a point 3, and finally this point 3 is comes back to point 1. Therefore, irrespective of how many times this three-fold rotation axis operates, you will have only 3 points. And to show this, I have got a model here. For instance, here I have got an axis which is a three-fold rotation axis, and this three-fold rotation axis is at the end of a triangle. Okay. So, now I have a triangle. Suppose this assume is a three-fold axis, it operates on this object, then it's a triangle which is indistinguishable with the triangle before. It operates again, it produces a triangle in identical orientation. So, just to make it clear here, so let me rotate it around so that you can see the triangle better. So, I have a three-fold axis and I rotate by 120 degrees, I land up with a triangle pointing upwards. I rotate again by 120 degrees, I land up with a triangle pointing upwards. Therefore, a three-fold axis leaves a triangle as a triangle before and after its operation. Similarly, the other important crystallographically compatible rotation is the four-fold rotation axis, which produces a rotation which is associated with a rotation of 90 degrees, and as before, suppose I start with the general point 1, then it rotates to the point to point 2, it rotates to the point to point 3, comes back to point 4, and finally the point 4 is rotated to point 1, which implies that space has closed on itself and we have only 4 points starting with a general point. And a six-fold rotation axis has a rotation of 60 degrees associated with it, and like before it leaves 6 distinct points in space. Starting with 1 I get 2, which is rotated to 3, which is rotated to 4, which is rotated to 5, which is rotated to 6, and this can be understood by taking an hexagon. For instance, if you talk about a hexagon, this hexagon has got 6-fold rotational symmetry. I can rotate by 60 degree, it looks exactly identical. I rotate it by 60 degrees again, it looks exactly identical. I rotate it by 60 degrees again and it looks exactly identical. Therefore, irrespective of how many times I rotate it 60 degrees, this entire hexagon will continue to look like an hexagon. So, this brings us back to some of the geometrical objects we had considered before. For instance, we have a cube. This cube has some beautiful symmetry, that it has got a mirror plane which is exactly splitting my cube into 2 parts. Therefore, if I only consider the right hand part of the cube along with the mirror, then I will get the left hand part back. Similarly, you can also visualize a mirror which is the diagonal mirror which is going vertically. So, I can visualize a diagonal mirror going into this plane vertically like this, and therefore, the right hand part of the cube would reflect to the left hand part of the cube. Additionally, you will notice that suppose I look along the top of a cube, then the top of the cube has a 4-fold rotational symmetry. So, let me show it from this direction. Is it clear from this perspective? Yeah. So, the cube has got a 4-fold rotation symmetry. In other words, suppose I rotate my cube by using this 4-fold rotation axis, it will rotate and look exactly like before. Similarly, the body diagonal of the cube has a 3-fold rotation axis. So, this is my body diagonal of the cube. So, let me maybe different. So, this body diagonal of the cube has 3-fold rotation axis. That means, if I rotate my cube, for instance, this is a cube oriented like this, and I rotate it along the body diagonal by an angle of 120 degrees, then it will look exactly identical. So, this rotation along this axis, for instance, now I am holding the body diagonal horizontally and I rotate it by 120 degrees, the cube looks exactly as before, and so forth. Therefore, these geometrical figures have beautiful symmetries, and we will see later that some of these symmetries are compatible, for instance, with translational symmetry, like this is tetrahedron has got a 3-fold axis which is vertical. It has additionally got a mirror plane which is going through in the vertical fashion right here. On the other hand, these symmetries, the symmetries of the icosahedron, which has got a 5-fold symmetry here, or the dodecahedron, which has also got a 5-fold symmetry here. So, this pentagonal face has got a connecting the opposite face is got a 5-fold symmetry, but these two objects, these two platonic solids, are not compatible with translational symmetry, and therefore, you would not find crystals having these symmetries. However, there are quasi crystals which have these kind of symmetries. So, coming back to our rotational symmetries, we summarize this slide by saying that in general, of course, any fold rotational axis is possible, but we restrict ourselves to the 1-fold, which means that basically you have a point which comes back to itself, which is equivalent to a 360 degree rotation, a 2-fold equivalent to a 180 degree rotation, 3-fold which is 120 degree rotation, a 4-fold which is associated with 90 degree rotation, and a 6-fold associated with 60 degree rotation. Therefore, we need to only consider these rotational symmetries when I am talking about crystals. In addition to these simple, or what you might call individual symmetry operators, there are other symmetry operators which are compound symmetry operators, and also there is a possibility of what is known as a combination of symmetry operators. We will try to distinguish these two. A compound symmetry operator is one which is a combination, but a fixed combination. In other words, it is a compound of two symmetry operators like a rotation and an inversion, and we have to notice here very carefully that this is not a rotation plus an inversion, but a roto-inversion, and I will try to distinguish the difference between a rotation plus an inversion and a roto-inversion, or equivalently a rotation plus an reflection as differentiated from a roto-reflection compound symmetry operator. So, what are the simple symmetry operators we have talked about so far? It is the translation, the mirror, inversion and rotation. And now we are talking about compound symmetry operators like the roto-inversion and the roto-reflection. It is to be noted that these symmetry operators, an entire symmetry operation acts before leaving a point. In other words, a roto-inversion is not a rotation plus an inversion. You cannot leave a point after rotation. You will have to start with a point, perform the roto-inversion and then leave a point. Similarly, if I am talking about roto-reflection, I have to start with a general point, I have to perform a roto-reflection and then leave the second point. While if I were talking about a combination of a rotation and a reflection, which is a possibility, then I can rotate. For instance, suppose I am talking about a combination of a 2-fold and a mirror. First, I will rotate by 180 degrees, I will land up with 2 points, then I can perform the mirror operation, which will take these 2 points to further 2 more points. But we will see what this roto-reflection does by actually considering equivalent things. So, to summarize this initial part of the slide, roto-reflection and roto-inversion are compound symmetry operators which do not involve translation. Both these take left-handed objects to right-handed forms. So, these are operators of the second kind which we had considered, which take an object to its enantiomorphic form. For generating point groups, which we will consider very soon, one of the operators, one of the two, which is the roto-reflection or the roto-inversion, is more than sufficient, and in general we will take up roto-inversion in the further examples we take up. Further, we can have compound symmetry operators which involve translation here and a mirror, which is known as the glide reflection, or we could have a translation in combination with a rotation, which is known as the screw symmetry operator. Therefore, we can have a glide reflection or a screw, and the important distinction between the two is that a glide reflection takes an object to its mirror form, while screw takes an object to the same form, which means a left-handed object in combination with screw will lead to an object which is only left-handed. In some cases, these compound symmetry operators, which we have considered, for instance the roto inversion, can be broken down into certain simple operations, but this does not mean that individual components are exactly identical to the components which is giving rise to the compound operator. This will become obvious when we perhaps consider an example. In other words, in a combination, unlike a compound, the individual operators express themselves fully, i.e. that is the first operator acts first, and then the second operator acts on the result of the first operation. That is what we call a combination, while in a compound you have a combined operator acting all at once. So, let us talk about one compound operator, which is a roto inversion, which will clarify the position. A roto inversion operator rotates a point and then inverts it all in one go. In other words, it does not do it in steps. And as I had pointed out, it will take a left-handed object to its right-handed form, and the roto inversion operations which are compatible with translational symmetry are the ones which we had considered, like in the case of simple rotation, are the 1 bar, the 2 bar, the 3 bar, 4 bar and 6 bar. In other words, the symbol used to describe roto inversion is a number like the normal rotation with a bar on top, which tells us that it is actually a roto inversion operation and not merely a rotation. So, therefore, the roto inversion operations I need to consider are the ones which are highlighted here, which are the 1 bar, the 2 bar, 3 bar and 4 bar and the 6 bar, and let us see how these operators act when you start with the general point. So, suppose I start with the right hand object above the plane, then the 1 bar operation implies that I rotate by 360 degrees. That means the rotation is 360 degrees. I come back here, but I do not stop there, I do not leave a point there, I invert immediately, and when I do the inversion, I land up with a left-handed objects below the plane of the slide. So, and of course, what will happen further if this roto inversion operates again? I will start with this left-hand point, rotate by 360 degrees. In other words, I will go again 360 degrees and come back to the left-handed object, but I will not leave a left-handed object below the plane of the board. I will immediately invert and land up with a right-handed object above the plane. That means I have closed space on itself. Therefore, an inversion 1 bar operator, which is exactly equivalent to an inversion, as we can compare it with an inversion operator which also leaves two points like this, one right-handed above the plane, one left-handed below the plane. Therefore, an 1 bar operator is exactly identical to the inversion, and it leaves only two objects and not more, not less, and these two points would be one right-handed and one left-handed. Similarly, I can talk about the 2 bar operator, which will again involve a rotation and an inversion, but all in one go. So, suppose I start with a right-handed green circle above the plane of the board, then I can rotate. What does a 2 bar imply? That the rotation associated with the 2 bar is 180 degrees, like in the case of a 2-fold. Therefore, I will rotate, I will go all the way and I will come back here, but I will not leave a point after the rotation. So, I will come back right exactly above the green circle, but after that I will invert. And so, no, sorry, I made a mistake here. So, what I will do is I will start with the green circle, I will go and rotate and come to a point which is 180 degree apart, and I will land up with a circle which is a green circle which is above the plane of the board. So, I have performed my 180 degree rotation, but I will not leave this point here. So, this is not a point which is to be left here, but I will immediately invert, which will mean it will take this point to a point which is below the plane of the board, and which is this red square which is minus, and it is a left-handed object. Therefore, when I have a 2 bar roto inversion operation, I start with a green circle, rotate it, do not leave a point, invert it and come back right below the green circle, which completes my roto inversion operation. We will see that it is actually this 2 bar is equivalent to a 1 followed by a mirror, which is nothing but an horizontal mirror. So, let us summarize the 2 bar operation, which we said is equivalent to a 1 by m operation or a mirror, horizontal mirror. Therefore, I start with a green circle above the plane of the slide, it rotates it by 180 degrees and we land up here. We do not leave a point, but invert right at the center, and therefore I will end up with a red square which is a left-handed object below the plane of the slide. And the symbol, as you can see, for all these operators is the 1 bar as a open circle, the 2 bar as a symbol like a twofold but with a circle in the center, a 3 bar, as you can see here, is a triangle with a circle in the center, the 4 bar operation is shown here, and similarly you can have a 6 bar. And this slides also explain to you that actually the concept of the compound versus the combination. So the 1 bar, the 2 bar, the 3 bar, the 4 bar and the 6 bar are compound operators, but we have just now seen the 2 bar can be thought of as an horizontal mirror. That means if I start with a green circle, actually put a horizontal mirror, the mirror being this M which is marked here, which is nothing but the red circle on the plane. Actually I will end up with these 2 points, and irrespective of how many times this mirror acts, I will end up with only 2 points, one left-handed, one right-handed, the left-handed being above the plane of the slide and the right-handed or the left-handed being below the plane of the slide. Therefore, I can break down this 2 bar operator as a combination of a 1 and an M. Therefore, this is my compound operator and this is my combination of a 1-fold and a perpendicular mirror. Similarly, I can think of a 3 bar operator as a combination of a 3 and an inversion, a 3-fold and an inversion. Therefore, when I am talking about a combination, then each one can act independently. For instance, I can start with a green circle, it can first act and leave a point here, then it can rotate and leave a point here, and finally this can rotate and come back to its point. I am not performing the inversion like a 3 bar operator, I am just performing the 3 which is mentioned here. Further, if I invert this, then I land up with these 3 red squares which are nothing but left-handed objects below the plane of the slide. Therefore, I can break down my 3 bar, which is a compound operator, into a combination which is a 3 and an inversion combination. Therefore, there is a possibility in some cases of decomposing my compound operator into a combination operators. However, we should always remember that a compound operator leaves a point after performing its complete duty, which is for instance in this case a roto and inversion, and then only you have an identity point. Let us try to understand, for instance, this 3 bar roto inversion operation with respect to a cube. For instance, where is a 3 bar roto inversion operation in a cube? And what do we see in a 3 bar roto inversion operation? There are 6 points which are created by this operation. So, I have a cube here, and originally I had pointed out that the body diagonal has a 3-fold symmetry, but actually it has got a symmetry which is higher than the 3-fold, because a 3-fold symmetry generates only 3 points, while we have just now seen that the 3 bar or the 3 bar roto inversion symmetry generates 6 points. Therefore, it is an operator having higher order as compared to a 3. So, the 3 bar operator is an higher order as compared to the 3-fold rotation axis. Now, let us try to understand where is the 3 bar operation and how we get the 6 points. So, if I consider my cube and my body diagonal, which is passing as you can see here. So, what does it do? If I start with the general point here, which is one of the vertices of the cube. So, I have totally 8 vertices for the cube. 2 of them I have taken away by putting my body diagonal line across that, and in addition to that I have 6 more vertices left. So, I can start with any one of those vertices, for instance, and when a 3 bar rotation axis acts on this, it will rotate it by 120 degree, which will take it here and invert it so as to produce this vertex from that. So, it will rotate by 120 degree, giving me this, and then it will invert it and produce this vertex from that. Therefore, when I start with this vertex, a 120 degree rotation will take it to this vertex, an inversion operation. So, the inversion center for this cube is the center of the cube, and that will take me to this point. Similarly, when I perform this roto inversion operation or the 3 bar operation again and again, I will obtain all the 6 vertices which are not contained in this body diagonal. Therefore, if you really want to describe the body diagonal symmetry of a cube, it is not just a 3-fold, actually it is a 3 bar roto inversion symmetry operation. Another compound symmetry operator is the screw axis, which is a combination of rotation and translation, and as before you perform a rotation and then leave perform a rotation and a translation and then leave a point. A screw axis operator rotates a point object and then moves it by a fraction of the repeat distance in one go. So, this fraction of the repeat distance is the fraction of the translational symmetry which we talked about. So, all crystals have a translational symmetry which we shall later on be correlated to the lattice parameter. Therefore, this fraction would be a fraction of the lattice parameter which we are talking about. And since typical crystals, for instance the copper crystal or for instance the magnesium crystal, all have translational symmetries of the order of angstroms, this fraction which of the screw axis, the translational fraction, is actually a fraction of that lattice parameter, which again is of the order of angstroms. Therefore, there is no external effect of this screw axis on the external symmetry or the growth form of the crystal. Therefore, you cannot observe a screw axis looking at the external shape of the crystal. The fraction by which the screw axis moved, called the pitch of the screw, and again like before we only consider the 1, 2 and 3, 4 and the 6, which are the translationally compatible rotational symmetries when you are talking about screw axis. The screw axis which we need to consider are the 2 subscript 1, the 3 subscript 1, the 3 subscript 2 and so forth as listed here, going up to 6 subscript 1, 6 subscript 2 to 6 subscript 5. And in this notation which we are seeing here, for instance this figure below shows a 2 subscript 1, the 2 is the usual two-fold rotation which is implied, and the 1 implies that the translational fraction is 1 by 2. So, suppose I have an screw operator which gives us m subscript n, which implies a rotation of m fold and a translational component which is n by m. So, this is my translational component involved in a screw axis. So, let us see the effect of what a screw axis can do. For instance, a 2-1 screw axis. So, a 2-1 screw axis is associated with two-fold symmetry, and the 2 subscript 1 implies the translational component is half the repeat distance or the translational periodicity. So, I start with a general point here. So, it will perform a 180-degree rotation from here to here, but as I told you, this is a compound operator and therefore, I will leave no point here, but I will translate by distance half my repeat unit. So, this is my repeat unit and I will only translate by half the repeat unit and leave a point here. I will progress with this set of 2-1 operations, which means that again I will rotate it and come here by 180 degrees, but again I will not leave a point here, but translate it by a fraction of half. Therefore, when I start with a point here, I land with a point exactly above the original point. Now, this symmetry operator connecting this point to this point to this point is the 2-1 screw axis, which is shown by a symbol as it is a lens with certain amount of tail on both sides. So, this is an extended symbol it has got. So, this is the effect of a 2-1 screw operator. Later on we will also talk about the other kind of screw operators talked about here, like the 3-1, 3-2, 4-1, 4-2, 4-3 etc. But we have to remember that all these screw operators move an identity point to its same form. It will not take a mirror form. That means, if I start with the left-handed objects, a screw operator will only leave left-handed objects as it goes along performing its rotations and translations. And as I pointed out, since the small fractional translations is not seen in the external growth shape of a crystal, the normal and the screw axis have the same effect on the external symmetry of a crystal or the growth form of a crystal. So, let us see how a 3-1 screw operator, for instance, acts. A 3-1 screw operator, you start at the point, it will rotate by 120 degrees, but it will not leave a point there, and it will translate by 1 by 3. Therefore, it will translate by 1/3. So, this is my 1/3 of the translational repeat distance, which is the total height t. Therefore, it will translate by 1/3, and from starting with this point 1, rotation by 120 degrees and followed by a translation of 1/3, I land up with this point 2. Further, again this operator will act, it will rotate by 1/3, which will take it to this point here, but it will not leave a point there, translate by 1/3, which will land up with point 3. This will again rotate by 120 degrees and it will come here, but it will not leave a point there, it will translate by this 1/3 and leave a point 4 finally, which is exactly translationally related to point 1 along the z direction. Now, a 3-2 screw axis rotates by a certain rotation, which is 120 into 2, but actually if you want to compare a 3-1 rotation axis with a 3-2 rotation axis, you will notice that you can perform the operations of a 3-2 axis, but you will land up with the points which are exactly related by a mirror operation M on the 3-1 screw axis. So, you can see that the symbol of the 3-1 axis is radiations like this, the 3-2 axis is exactly the mirror symmetric symbol, and so are the effects on the points left out by a 3-1 or a 3-2 screw axis. So, a 3-1 axis leaves these set of points, while a 3-2 axis is exactly like a 3-1 axis, but if you consider 3-1 as a right handed screw, then 3-2 is a left handed screw, which again leaves two set of points like 1, 2, is that you start with one point, you rotate by the amount given by the rotational symmetry, which is written as the main part of the symbol, then you translate by a fraction, which is a fraction of the repeat unit. So, in the case of the 4-1 screw axis, for instance, you will rotate by 90 degrees and the translational component will be 1/4 of the total translational symmetry, which is 1 unit along the z direction. So, and similarly like before, the 4-1 rotation axis is related to the 4-3 by a mirror plane, and the symbols are also related by a mirror plane as shown here in the above view graph. Similarly, we have a 4-2 axis which has got a symbol here, and you can see that in the 4-2 axis you have a 90 degree rotation and a translational component which is 2/4, which is half. So, in effect all these rotation axes are very similar in their effect, and we need to consider them when we are talking about symmetries of crystals. Okay. And we will return to this concept later. For instance, the 6-3 screw axis is at the heart of, for instance, the hexagonal closed pack crystal to be called hexagonal closed pack crystal. So, some of these concepts we will return to later, but once we understood one screw operator, all the others are very similar in their effect in leaving a set of points which are all either left handed or all are right handed operations. Another, we talked about a compound operation which is the glide reflection operator, and in the glide reflection operator you start at the point, there is a translational component which is a fraction of the translation. For instance, it could be a fraction of the translation along, for instance, the x axis, and you reflect. For instance, now suppose my translational component along a certain component is this is my translational periodicity, say for instance A, then my glide reflection operator is a combination of a translation and a reflection. So, at the heart of a glide reflection operator is a mirror. So, this is my mirror plane, and what does a glide reflection operator do? You start with a point which is, for instance, a right handed object above the plane of the mirror plane. It translates by a fraction of the periodicity. Now, for instance, this my periodicity along this direction is A, then my translational component is A/2. Therefore, this is called A/2 glide. Therefore, you translate by half and reflect. Therefore, you land up with a mirror form of this object, which is a left handed form and below the plane. Further, if this glide reflection operator acts again, then you will move this point and reflect, and you land up with a point exactly like the right handed object above the plane, but now moved by a point by lattice parameter A. Now, this implies that if I have a glide reflection operator, then it will leave half its points as left handed objects and half the points would be right handed. And not only that, as the like in the case of the screw operator, when the glide reflection repeatedly operates, it moves a point in space, and therefore it fills up along one direction an infinite set, creates an infinite set of points as it repeatedly acts. But as you can notice, the number of points within this unit cell or the repeat distance, now this is my repeat distance, is only 2. There is one here and there is one here. One is a right hand object, one is a left hand object. In other words, even though the screw, and which we can go back and see now, for instance, the screw, if it keeps on acting, would create an infinite number of points, but the number of points within this repeat distance T is only 2, one here and one here. And similarly, for the glide reflection operator, the number of points within the repeat distance is only a finite number, though if these glide reflection operators act, they keep on acting repeatedly and create an infinite set, the number I need to worry about is the number which in a single repeat unit or the single unit cell, as we will see later. So, but there are very many possible type of glides which are listed here, though we will not be going into detail. It is worthwhile to know that these kind of glides exist. For instance, you could have a glide with the translation component along the one direction. You could have a translation component for this is along, for instance, the x direction. This could be a translation component along y direction, or you could have a glide operator which has a translation component along the z direction. We could also have what are known as diagonal glides, which are given a symbol n, in which case the translational component is again half, but it is an average of the translation along x and y direction both. So, this can be seen here. So, for instance, this is my A glide, for instance, I can show here. So, this is my A glide which takes which has a translational component along the A direction. You could have, for instance, a diagonal glide which has a translational component, like you can see an A plus B by 2, that means it is not along the phase diagonal, or you could have, as we have seen before here, a diamond glide in which the translational component is 1/4 and not half, as in the case of the axial glide or the diagonal glide. To summarize glides, we got axial glide, diagonal glide and diamond glides, all of which basically take an object with an enantiomorphic form and involve a translation. Now, the next important concept in crystallography is the concept of point groups, and a more advanced concept, which of course we will not take up in this course in detail, is the concept of space groups. But it is worthwhile to be exposed to such terminology, because when somebody reads an official text on crystal structures, you will be exposed to these concepts like point groups and space groups, and especially these point groups are very, very important from the point of view of properties of crystals, as we have noted before. So far we have seen various kinds of symmetry operators, and we know that they leave a finite set of points within a unit cell. But are there combinations of symmetry operators which are possible? We have actually seen some examples. For instance, we have seen a combination like 1 by m, or the 3 dot I, which means the combination of 3 and inversion. And we have to note that in general, of course, all possible combinations are not allowed. There are only certain distinct combinations allowed which can leave a finite set of points in space, like the case of the normal operators, which also leave a finite set of points in a unit cell. Therefore, there are only certain allowed combinations of symmetry operators, and it so happens luckily that this number is not very large, and there are only 32 allowed combinations of symmetry operators which are not known as the 32 point groups. And if you are talking about those symmetry operators which involve the translation like the screw or the glide, then there are 230 allowed combinations which are called the 230 space groups. In the point groups, you stay around a point, you do not move the point from one place to another. But suppose I am talking about those symmetry operators which involve translation like the glide or the screw, that means that I am going to move the point, and if you include those symmetry operators, 230 such combinations are allowed, which are known as the 230 space groups. It is very, very important to have these numbers in mind, because we will later on be exposed to the concept of 7 crystal systems, and in fact, and also another additional concept known as the 14 Bravais lattices. The 14 Bravais lattices are created purely by translational symmetry, but it is interesting to note that if you are talking about these 230 space groups and those which are compatible with, and those among those which are consistent with lattices, then these 230 space groups will lead to the 14 Bravais lattices. So, let me summarize this rather complicated slide, that if you are talking about symmetries acting at a point, then the allowed combinations will lead to 32 point groups, and we will see some, at least couple of examples of what we mean by allowed combinations. Then among these, those symmetries which survive, when I am talking about symmetries of lattices, are 7 in number, which are nothing but which correspond to the 7 crystal systems. Similarly, suppose I am talking about allowed combinations of symmetry operators which involve translation, then I land up with the 230 space groups, and out of those, if I am only considering those symmetries out of these 230 symmetries of the space groups, those which are compatible with lattices, then I land up with the number 14, which are known as the 14 Bravais lattices. Of course, one could land up with the 14 Bravais lattices, as we shall see, that by purely considering translations. Okay. So, this is a what you might call a real look ahead or a very difficult concept, but here we just want to introduce the important what you call essentials of these concepts, because some of these would form the basis of some of the descriptions you would read. For instance, when you are studying about crystal structures in an international tables, or you are studying about a report about some crystal structures. Okay. So, for instance, suppose I am talking about allowed combinations. One such allowed combination is a 4 mm symmetry, and for instance, suppose I am talking about a disallowed combination. For instance, a 2-2 symmetry with 15 degrees included angle would be a disallowed combination. So, let us see how is for instance, how can we talk about an allowed combination as 4 mm. Suppose I am talking about a 4 mm symmetry. Here I am talking, though the symbol does not tell all the details about this allowed combination, what we exactly mean by this 4 mm symmetry is the fact that you got a 4-fold, you got one vertical mirror and one diagonal mirror, and the orientation between the two mirrors is 45 degrees. So, these are things which are implied, which are not explicitly written out, but which are implied in the symbol. So, when I am talking about 4 mm, actually what we are talking about is 4 fold in combination with M1 and M2. If I call this M1, the diagonal mirror will be M2. And as you can see, the line of intersection of the two mirrors M1 and M2 is the line of the rotation axis, which is the 4-fold. Now, suppose I start with a general point, which is a right-handed R drawn here, then my 4-fold will lead me from this green to this green to this green, and finally to the 4th green, and finally it will close space on itself. But this mirror, for instance, will produce a left-handed R, and this horizontal mirror will take this to this right-handed R. In other words, how many ever times this 4 mm symmetry acts, either individual mirrors or this combination or the 4-fold, you will notice that I will end up with 8 objects only, and if I start with a point, I will end up with 8 points. Or if I am talking about this right-handed objects R, then I will have 4 right-handed objects, then and I would have 4 left-handed objects, which are shown in orange color. Therefore, we know from the mere action of this operator 4 mm that it is an allowed combination, because first of all I will end up with a finite number of points starting with, or a finite number of objects starting with one object R, a green R for instance. I will end up with 4 green R's and 4 red R's or 4 orange R's. Therefore, I have only 8 objects if I start with one object. Therefore, I can clearly see 4 mm is an allowed combination as far as crystals go. Now, another allowed combination is shown here, for instance, which is the 6-2-2, and these combinations are typically written out using what is known as the Harman-Mogwan symbol, which is a shorthand notation for these symmetry operations. And in the second example shown here, as I had pointed out before, if I am talking about two folds, any arbitrary angle between the two folds is not allowed, but a 30-degree included angle, for instance as shown here, is an allowed combination. And in that case, suppose I start with two folds and an included angle of 30 degrees, then I will land up with, as you can see here, 12 two-fold axes, and which automatically implies that there is a 6-fold rotation axis, and the total Harman-Mogwan symbol for this combination is 6-2-2. And I can actually perform an experiment like I had done with a green R right here. I can put one of those objects here, and I can confirm to myself that actually I will land up with a finite set of objects if I am talking about this allowed combination of 6-2-2 symmetry. There could be couple of reasons why a symmetry combination is disallowed. One of the reasons is that suppose I talk about two mirrors at 15 degree apart, then this mirror will this mirror will rotate it to this mirror, and this will rotate it to this mirror, and so forth. You will land up with an array of rotation axes. For instance, this is now. So, suppose I am talking about disallowed combinations, and going back to the previous slide, we had talked about allowed combinations, and one small error here is that these are actually rotation 1 and rotation 2, which are nothing but two-fold axes, and here we are considering disallowed combinations of symmetry operators. In fact, if you randomly, you have already seen the number of allowed combinations is only 32 for symmetry operators which act around a point. So, that implies that most of the other combinations are disallowed. So, we cannot have a random combination of two symmetry operators which will leave space closed. For suppose I talk about a combination like a two-fold axis, another two-fold axis which are 15 degree apart, then this two-fold axis will rotate it to another two-fold and so forth, and I will have an array of two-fold axes as shown here. But this combination of two folds would imply a 12-fold axis perpendicular, and if we go back to the place where we had said that 12-fold is not a symmetry which is crystallographically compatible. Similarly, another reason why a particular combination may not be allowed is that the combination would start producing an infinite number of symmetry operators, which also mean that if you start at the general point, you may land up with an infinite number of symmetry operators. Such example would be two two-fold axes with an included angle of about 7 degrees. Then you will land up with an infinite number of points starting with one point, and therefore we shall restrict ourselves to only the allowed combinations which are crystallographically allowed. Now, let us briefly talk about the 32 point groups, which are nothing but the 32 ways in which symmetry operators can combine and leave. If one start dealing with a point, gives you a finite number of points in a region of space. So, these 32 point groups in fact can, if you consider them to have the highest symmetry which is compatible with lattices, then you will end up with 7, which we pointed out, where the symmetries of the 7 crystal systems, which we will take up later during the course. Though, and the important point is that at this we can actually associate these point groups, like you have an allowed combination like 2 3, the 4 bar 3m, the m 3 bar, the 4 3 2, and the 4 by m 3 bar 2 by m. These point groups come under the cubic class. In other words, if I have a cubic crystal, then it has to fit into one of these symmetry classes. And typically, if you take, for instance, we will consider examples like copper crystals, or for instance polonium crystal, or for that matter iron crystal. These would have the highest allowed symmetry, which is 4 by m 3 bar 2 by m symmetry, while it is possible that there are certain lower symmetry cubic crystals which does not have the full or the highest symmetry allowed for a cubic class. Similarly, we can talk about hexagonal crystals having the highest symmetry, which is 6 by m 2 by m 2 by m, or any one of the lower symmetries which is allowed for a hexagonal crystal. And by noting all these different point groups and the different crystal classes into which, or the crystal systems to which they belong, we can actually sort of come out with a characteristic symmetry or a symmetry which is basically required for a crystal. For instance, if you have a cubic crystal, it needs to have 4 3-fold axes. A hexagonal crystal needs to have at least 1 6-fold axis, and that is all possible. There is only 1 6-fold axis. A tetragonal crystal needs to have at least 1 4-fold axis. A trigonal crystal has only 1 3-fold axis, and if a crystal ends up having 2 3-fold axis, then it will end up having 4 3-fold axis, and actually then it will start coming into the cubic class and not in the trigonal class. Similarly, an orthorhombic crystal has 3 perpendicular 2-fold axis. A monoclinic crystal has 1 2-fold axis. A triclinic crystal at best can have an inversion symmetry, or at worst can have only translational symmetry. In other words, if a crystal doesn't even have translational symmetry, it cannot be called a crystal, then it will be classified as an amorphous material. On the other hand, if it at least has translational symmetry, it will qualify to be at least a triclinic crystal, and if any more symmetry is possible in the system, then it can climb up the ladder and go all the way up to the cubic crystal, which is a crystal having very high symmetry, and it can have a symmetry up to 4 by m 3 bar 2 by m.